Hey everyone, welcome back to my channel. Today we're diving deep into one of the most game-changing concepts in machine learning, momentum-based gradient optimizers. But before we jump into momentum, let's quickly understand what optimization actually means in machine learning. Imagine you're hiking down a mountain in thick fog. You can only see your immediate surroundings and need to find the lowest point, the valley. That's essentially what our machine learning models do when they're trying to minimize the loss function. Optimization in ML is the process of finding the best parameters for our model that minimize the error or loss. Think of it as teaching our model to make better predictions by adjusting its internal weights and biases. Let's start with the classic gradient descent algorithm. This is our baseline, the hiking technique where you always step in the steepest downhill direction. The formula is beautifully simple. New parameters equals old parameters minus learning rate times gradient. But here's the problem. Classic gradient descent can be painfully slow and inefficient. It's like a hiker who forgets every step they've taken. No memory, no momentum, just blindly following the immediate slope. In landscapes with steep ravines, which are common in deep learning, vanilla gradient descent zigzags back and forth, making very little progress toward the actual minimum. This is where momentum comes to the rescue. Think of momentum as giving our optimization algorithm a memory. Imagine instead of a careful hiker, we have a heavy ball rolling down the mountain. This ball doesn't just respond to the current slope, it carries forward the momentum from all its previous movement. In mathematical terms, momentum accumulates gradients from previous steps, creating a velocity term that helps us navigate through flat regions faster, reduce oscillations in steep ravines, escape shallow local minima, and converge faster to the global minimum. Look at this beautiful comparison. See how momentum-based optimization creates smoother, faster convergence compared to vanilla gradient descent. Now let's understand the key hyperparameters that control momentum-based optimization. First, we have the learning rate alpha. This controls how big steps we take. Too big, and we overshoot the minimum. Too small, and we crawl toward the solution. Typical values range from 0.001 to 0.1, but this needs careful tuning based on your specific problem. Next is the momentum coefficient beta. This is the magic number that controls how much of the previous velocity we retain. Beta equal to 0 means no momentum, just vanilla gradient descent. Beta equal to 0.9 means we retain 90% of previous velocity. Common values are 0.9 or 0.99. Higher beta values give more momentum, but can cause overshooting. It's all about finding the sweet spot for your optimization landscape. Let me break down exactly how momentum-based gradient descent works step by step. Step 1. Initialize our velocity vector to 0. This will accumulate our momentum. Step 2. For each iteration, compute the gradient of our loss function with respect to current parameters. Step 3. Update velocity using momentum formula. This is where the magic happens. Notice how we're combining the previous velocity scaled by beta with the current gradient scaled by learning rate. Step 4. Update parameters using the accumulated velocity. The beauty is in this accumulation. Each step builds upon the history of all previous steps, creating smoother, more intelligent movement through our optimization landscape. Now here's where it gets really interesting. There are several flavors of momentum-based optimizers, each with unique advantages. First up, classical momentum, also called heavy ball method. This is what we just covered. Simple, effective, and widely used. Next, Nesterov accelerated gradient, or NAG. This is momentum with a twist. Instead of computing gradient at current position, we compute it at the anticipated future position. It's like looking ahead before you leap. NAG often converges faster and with better stability. Then we have ATOM, adaptive moment estimation. This combines momentum with adaptive learning rates for each parameter individually. And RMS prop, which adapts learning rates based on recent gradient magnitudes. Each has its strengths: classical momentum for simplicity, NAG for speed, ATOM for adaptive learning rates. Let me show you why momentum-based optimizers are absolute game changers in deep learning. Advantage number 1, dramatically faster convergence. Look at this comparison. Momentum reaches the minimum in half the iterations. This means faster training, less computational costs, and quicker results. Advantage 2, massive reduction in oscillations. See how smooth this trajectory is compared to vanilla gradient descent? This stability is crucial for consistent training in deep neural networks. Advantage 3, better escape from shallow local minima. The accumulated momentum helps push through small bumps in the lost landscape. This is especially important in complex neural network optimization, where local minima are everywhere. Advantage 4, superior performance in high-dimensional spaces, which is exactly what we deal with in deep learning. Now, momentum isn't perfect. Let me share the main challenges and how to handle them. Challenge 1. Hyperparameter tuning can be tricky. Too much momentum and you overshoot. Too little and you lose the benefits. Pro tip: start with beta equals 0.9 and learning rate equals 0.001, then tune based on your loss curves. Challenge 2. Momentum can cause overshooting, especially near the minimum. Solution: use learning rate scheduling. Reduce learning rate as training progresses. Challenge 3. Momentum requires storing velocity vectors, increasing memory usage. For very large models, this can be significant, but the performance benefits usually justify the cost. Here are my top practical tips. Always visualize your loss curves. Use TensorBoard for monitoring. Start conservative, then tune aggressively. Consider different optimizers for different layers. Let's see how to implement momentum-based optimization in practice. Want to implement from scratch? Here's the core logic. Similar implementations exist in TensorFlow, JAX, and all major deep learning frameworks. All right, let's wrap this up. We've covered a lot of ground today. Here are the key takeaways. Momentum-based optimizers add memory to gradient descent, creating faster and more stable convergence. The momentum coefficient beta controls how much history we retain, typically 0.9 or 0.99. These optimizers excel at navigating complex loss landscapes common in deep learning. While hyperparameter tuning requires care, the performance benefits are substantial. I challenge you to implement momentum-based optimization in your next project and compare the results. If this video helped you understand momentum-based optimizers, smash that like button and subscribe for more deep learning content. Next, we're diving into Add-a-Grad Optimizer. You won't want to miss it. Thanks for watching. Keep optimizing, and I'll see you in the next video.